If you have ever taken a physics class, you have likely heard the classic explanation for why it is difficult to measure the quantum world. It usually goes something like this. To see an electron, you have to bounce a photon of light off of it. But the moment that photon strikes the electron, it knocks it away like a cue ball breaking a rack in billiards. Because that collision physically transfers energy, you have permanently altered the electron's speed and trajectory. By the time the photon bounces back to your detector, the electron is already somewhere else, moving at a new velocity. You can never know where it was and how fast it was moving at the exact same time. This physical interference is a real phenomenon. In complex systems, the act of measuring something often disrupts it. Physicists define this as the observer effect. But there is a major problem with this explanation. The observer effect is distinct from the Heisenberg uncertainty principle. Conflating the two concepts is one of the most pervasive misconceptions in popular physics. When Werner Heisenberg formulated his principle in 1927, he was not describing a limitation of our laboratory equipment. His mathematics revealed that a particle cannot possess both a precise location and a precise momentum at the exact same time. This holds true even in a perfectly isolated vacuum, billions of light years from the nearest telescope, with 0 observers present. The confusion stems from our daily intuition. We are wired to think of an electron as a microscopic marble, a solid physical object with a definite edge. But at the quantum scale, particles behave as waves. Wave mechanics dictate that any localized state must possess a range of frequencies. This structural property is an inherent part of how quantum objects exist in space. To understand why uncertainty is baked into the universe, we have to drop the billiard ball analogy and look at the pure mathematics. A quantum state is best described as a wave packet. This graph shows a Gaussian probability distribution. The horizontal axis is position space. That tight, narrow peak in the center represents a highly localized particle, meaning we have a very accurate measure of its exact physical location. To find the momentum of this wave, we have to determine its wavelength, and to extract the wavelength from a localized pulse, we apply a mathematical operation known as the Fourier transform. These two graphs represent Fourier conjugates. They are mathematically linked by a strict inverse relationship. If you try to squeeze the position curve to pinpoint the exact location of the wave, the momentum curve is forced to expand outward and flatten out. No matter how you manipulate the wave, you cannot make both curves narrow at the same time. The product of their variances equals exactly 1/2. This is a rigid law of mathematics, completely independent of physics. Physics enters the picture when we apply the de Broglie relation to this math, which ties a particle's physical momentum to its wavelength. We achieve this by multiplying our Fourier variance by the reduced Planck constant. That simple substitution gives us the famous uncertainty principle equation. Delta x times delta p is greater than or equal to h bar over 2. Heisenberg simply mapped a mathematical rule onto physical reality. To build a perfectly localized wave packet, you have to add together an infinite number of different frequencies. Because each frequency corresponds to a different momentum, a localized particle inherently possesses an infinite range of possible momenta. The uncertainty is established long before any observer enters the room. We can see exactly how this mathematical law governs reality by looking at the simplest building block of matter, the hydrogen atom. According to classical physics, a hydrogen atom should not exist. The negatively charged electron is fiercely attracted to the positively charged proton at the center. Under classical rules, that electrostatic pull should drag the electron straight into the nucleus, collapsing the atom instantly. But as the electron gets pulled closer to the proton, it shrinks its position space. And as we saw with the Fourier transform, tightly constraining an electron's position forces a massive expansion in the uncertainty of its momentum. In physical reality, this uncertainty manifests as rapid fluctuations in speed. The resulting kinetic energy pushes outward against the electrostatic attraction until the two forces lock into a stable equilibrium. This balances the electron, but it raises an obvious question. If the uncertainty principle applies to all matter, why doesn't the proton at the center smear out into a massive cloud? The physicist Richard Feynman resolved this by demonstrating that mass acts as a reverse scaling factor for quantum uncertainty. Momentum is mass multiplied by velocity. This means the total momentum uncertainty is distributed between how heavy a particle is and how fast it is moving. A proton is roughly 1,836 times more massive than an electron. It carries entirely different physical weight. Look at this rearrangement of the equation. Because the mass variable sits in the denominator, a massive increase in weight scales down the overall uncertainty. The weight of the proton absorbs the uncertainty, allowing its positional spread to shrink. Because of this ratio, the heavy proton remains tightly localized at the core of the atom, while the incredibly light electron is forced to smear out into a vast probabilistic cloud. Heisenberg's principle provides the counterpressure required to stop atoms from collapsing. This mathematical tension is what ultimately allows solid objects to occupy space. From the width of a hydrogen atom up to the structure of the human body, the standard uncertainty principle operates flawlessly. It forms the load-bearing mathematical framework for our physical reality. We even rely on it for modern cybersecurity. In quantum key distribution, if a hacker tries to intercept a signal, the act of interacting with the system forces the wave state to collapse, instantly alerting the defenders. The uncertainty is practically impenetrable. But if you push physics to its absolute most extreme frontiers, even Heisenberg's flawless mathematics begin to break down. To pinpoint a particle's location with extreme precision, you have to hit it with particles carrying massive, highly concentrated amounts of momentum. Thanks to general relativity, we know that energy and mass are equivalent. At these immense momentum levels, the kinetic energy itself generates enough gravity to physically warp the surrounding spacetime. To account for this intersection of quantum mechanics and gravity, physicists had to update the math. This required a new framework known as the generalized uncertainty principle. This updated formula looks like Heisenberg's original, that adds a critical second term factoring in gravitational curvature. This single term establishes a mathematical floor, a hard limit on measuring space. We call this absolute minimum the Planck length. Under this generalized principle, infinite precision is physically impossible. You cannot zoom in forever. Eventually, the very act of trying to resolve a smaller distance generates so much gravity that spacetime itself becomes unreadable. The Planck length represents a hard stop for the universe. At this scale, the geometry of spacetime and the laws of momentum converge to set a final limit on what can be measured.